Welcome back to physics. So I want to go into a couple of things. First was talking about IRV tables and the way that they're used in describing circuits. So the idea with circuits is you want to figure out some component of it, so either current or resistance or voltage at a particular point. And this gets tricky as you get into more complex circuits, but the math is not tricky, it is just thinking about it is tricky. So the IRV tables are one way to help you think about this. So let me think about a circuit. So I'm going to have a circuit, it's going to have a battery. So battery is going to be composed of cells. In this case, I'm going to have a positive side and a negative side. A battery acts to pump electrons up to the positive side, from the positive side to the negative side. I have connected to that some wire, and then I'll have it go through a resistor and then continue. So remember how this is going to work. So I'm going to have electrons. Electrons are going to flow naturally, get away from other electrons. They're going to flow through the resistor and reach the positive side, and my battery is going to pump those electrons from the positive side to the negative side. So if I have a battery that's, I don't know, 10 volts, that I can use a loop rule. So it's going to come up a bunch. So I can use a loop rule which says if I start here, any path I take returning to that point, I will have a voltage that adds up to 0. So what that means, I go across here, I'm going to gain 10 volts going across my battery. And then as I follow along, I must lose 10 volts coming across that resistor to get back to here. So I know this must be 10 volts here. So anyway, if I have a resistor, which I don't know, say it has 10 ohms, and I know the voltage drop across here must be 10 volts, then I can figure out what the current is, or how much electricity is flowing per second, or the charge per second going through there, so I can figure out the current, because I know current times resistance is going to equal my voltage. So this is my IRV equation, so it's also known as Ohm's law, so it describes a relationship. We're going to deal with things only that are ohmic, so we're going to assume this is true. The beauty about Ohm's law, though, is it's going to be true at every point. So any point I pick, right, including a piece of wire, right, but any point I pick, and here I'm interested in the resistor, that this is going to be true. If I pick a point on the wire, right, what's my voltage drop in the middle of a wire? Well, 0. What's the resistance? Well, 0. So it's not as helpful, but it holds true at every point, so we get to use it again and again and again. And that's all we're going to do. We're going to use it over and over again. Right? So in this case, I could plug in some numbers. So I know my voltage is 10. I can solve for current. So current is going to be voltage over resistance, and convince yourself that's going to be 1 amp in the end. The phrase I like is the one that says volts pushes amps through ohms. Okay. So the voltage, I'm going to think of that as the height of my dam. So that's the force, or the electromotive force, that's pushing electrons. Is going to push those electrons. So amps, current, is the flow of electrons, and the restriction is going to be some sort of resistor, in this case a specific resistor. Okay, so two of the things that we're going to do. So we're going to take resistors and we're going to put them into series. So I can have more than one resistor. I can put them one after the other. And when we do this, my total resistance now is going to be the sum of each of the individual resistors. Right? Importantly, though, think about this, that how is current and voltage affected? Well, voltage is going to drop across each of these, and it's going to depend on the resistor, but also current, though, is going to be the same in here, right? So however many electrons flow into this one must flow through the next one. So my current between 1 is going to equal 2 is going to equal, so on. So if I had however many I had in series, right? So the current through resistors in series is going to be the same. The second thing, we're going to look at our resistors in parallel. So I can have a resistor. So an electron coming in has to make a choice, has to either go to the through the top loop or through the bottom loop. So first thing is resistance. So now I have two different paths, and my total resistance is going to be less than what I started with. And the way we do this mathematically is my total resistance. 1 over my total resistance is going to be 1 over resistance 1 plus 1 over resistance 2, and so on. So I can figure out the total resistance, and my total resistance is going to be less than those two individually. And my current gets split, right? So my current is not going to be the same, but my voltage will be. So the voltage across 1 is going to equal the voltage across 2, and if I had more, so on. So these are the two things that we're going to use. So we're going to have something in series, which I can calculate an equivalent resistance, and I know the current across each of those must be the same, or I have something in parallel and I can calculate an equivalent resistance, and I know the voltage across those will be the same. So these are the two things that we're going to use to look at more complex circuits. Okay, let's look at a circuit. So I'm going to have something, let's make a new circuit. So let's see, I'm going to put a battery here, has a positive side, a negative side. I'm going to have this flow along. It's going to come to a resistor. It's going to come back. Let's make this 15 volts. Why not? And we'll make our resistor. We'll call this 10 ohms. 10 ohms. Let's put a second resistor in here. It'll make it a little more complex. So make it a resistor 2. We'll make this 5 ohms. Okay, so now I've got 2 resistors. So what I can do is I can figure out the current or voltage or resistance at any point here, including at this resistor or at this resistor, or if I wanted to at the battery. And we're going to use IRV, we're going to use Ohm's law again and again, but let's think about how we use it. So one way to simplify this is that instead of having 2 resistors, I'm going to replace them with one equivalent resistor, right? So I know my equivalent resistor. If I have 2 in series, I can simply add these together. So I could write another circuit, which now is going to have one resistor that has 15 ohms, right? So I could go to the bother of drawing this. This is going to be one resistor. So this is going to behave the same as if I had a 15 volt battery and a 15 ohm resistor on this side. So I think you could do the math from here if you on your own if you wanted to, but let me help you structure it so when it gets more complex it's a little bit easier. So here's what I'm going to do. So I'm going to make a table. In this table I'm going to keep track of the current, the resistance, and the voltage, right? IRV. I'm going to keep track of IRV, and I'm going to keep track of that for resistor 1. So I'm looking at resistor 1, when I'm looking at resistor 2, and then for my total circuit. So we know some things. Let's fill in what we know. So I know resistor 1. Resistor 1 has a resistance of 10 ohms. Resistor 2 has a resistance of 5 ohms. We calculated the total resistance is 15 ohms. I don't know the current, but the voltage drop across here. So if I start here in my loop, 0, I gain 15 volts. I must lose 15 volts to get back to 0. So my voltage drop must be 15. And from this, I can use IRV, right? Current times resistance equals voltage. I can figure out that this must be 1 amp. And now I'll think about my circuits that are in series. So my circuit's in series, so however much current I have here, that same amount of current must flow into the next one. So this current, however many electrons I have pushing through this one, I'm going to have the same number of electrons pushing through that next one. All right. So again, we define current as a flow of positive charge, so I'll draw things going, in this case, clockwise. In reality, it's the flow of negative charge. Thank you, Benjamin Franklin. So I know the current is going to be the same, right? So here we go. I know this much. So now I can calculate everything else, right? So now I know the voltage drop across R1 must be 10 volts, and the voltage drop across R2 must be 5 volts. And look, it adds up, right? So I should be able to loop rule here on my original circuit. I go around, I gain 15 volts, I lose 10 volts, I lose 5 volts, and I get back to 0. So the table is a handy way to think about things and help you figure out more complex circuits. So let me do one in parallel, and then I'll set you up on one that's a little bit more complex, and hopefully you're getting the idea by that point. Okay, so here's do one that's a little bit more complex. So let me take one that's got a battery, and let me see, I'm going to do parallel, right? So I'm going to put one here, I'll put another resistor here. This can come back and return. This is the negative side, this is the positive side of my battery. Current's going to flow this direction, and electrons are going to flow the opposite direction. Right? So let me make this resistor 1. What do I want to do here? Let's make this 10 ohms. Let's make this just 2. Let's make this 20 ohms. And then I'll make it 12 volts. Right? And just like your car battery. So now I can do the same sorts of steps. I just have a little bit different math. Right? So I can go through and I could come up with an equivalent resistance, and I could draw a new circuit that's going to have that one equivalent resistor there, and function is going to behave the same. So I'm going to still have my 12 volts here. And remember how I get to this. So now I'm going to get to this by doing the inverses. So 1 over my R total is going to be 1 over R1 plus 1 over R2, which is going to be what? 1 over 10 plus 1 over 20, which is what? 3 over 20. So I take the inverse of that. Be careful. So you need to take the inverse at the end. I have 20 over 3 horseshoes. Right? So the equivalent resistance here is going to be whatever comes out to pretty close to 7 ohms, or 20 over 3. So if I wanted to, I could find the current, and then I could figure out what the current and voltage is across these. But let's do a table to organize our thoughts, right? You could probably do this without the table for this one, but the organization really helps when you get to things that are more complex. Right? So I'm gonna, let's see, I'll make this one voltage, resistance, and current, and I'm gonna worry about what's happening at R1, worry about what's happening at R2, and then for my total one. Let me switch to a different color, right? So we've already done some of these, right? So I know my resistance here is 20 over 3. My resistance for R2 is 20. My resistance here is 10. I can use a loop rule here to figure out the voltage drop. Right? So if I start here, I gain 12 volts as I go across that battery, then I must lose those 12 volts to get back to 0. So I know this must be 12 volts. And I can use IRV, right? So I want to find what I want to find. Find current here. I know resistance and voltage. So my current is going to be my 12 volts times 3 over 20. I should have done simpler math. Was that going to be 36 over 20, or I'm calling that 1.8 amps. Well, now I know the current is flowing through here, but notice my current is going to get split here, so I really don't know what the current is here. However, I do know the voltage, so remember, things in parallel, the voltage is going to be the same, and I can think about this in terms of loop rule, right? If I start here, I gain 12 volts. If I go this way, that's the only resistor. I must lose 12 volts there, but I could take a different path, and I must lose the same 12 volts going across that. So my resistors in parallel, the voltage is going to be the same, so I know each of these must be 12 volts. And now I can IRV some more. I can figure out the current. I should have picked easier numbers. The current at 2 is going to be what? V over R, or 12 over 20, or 0.6. So I get 0.6 amps, and the current at the first one, this is going to be V over R, or I'm going to have 12 over 10, or 1.2. Notice I can check these add up, right? So, and this is the junction rule, so Kirchhoff's second rule, so loop rule is really handy. Junction rule is also handy, says that whatever current I have flowing into a junction, I must have the same amount of current flowing out of it, right? Makes sense. If I'm pumping water into a pipe, I must have the same water coming out, even if I have 2 exits that happen. So here, the current going through 1 and the current going through 2 adds up to the total current, so that's good. So this all works out, so I have confidence my answers are correct. Okay, let me get you started on one that's a little bit more complex, right? So these you could probably do without too much assistance, but we can think about things a little bit more complex. So I'm going to just get this one set up for you and leave you to think about it, but it's the same idea and the same strategy. So we'll try to simplify our circuit as we can, and then identify each of these different components separately. So let's go crazy. So here we go. Let's put a resistor here. Come in there. We go another parallel resistor there. Let's put another one in series here. Why not? Right. So I'm going to call this R1. I give this some value. I don't know, 10 ohms. Call this R2. We'll give it, I don't know, 5 ohms. This one R3. We'll give it, I don't know, 6 ohms just to make it funky. And with this R4, and we'll give this, I don't know, 7 ohms. And we'll make it, I don't know, 18 volts, so it'll be like a tractor trailer battery. Right? This is my positive side, this is my negative side. My electrons will flow this way, my current flow positive charge goes the opposite ways. Whew, right? Some steps here to think about. So this is the way I tackle these, is I say, well, I'm going to take this one. This is like the most nested. It's the most innermost of these. And I'm going to simplify this. I'm going to draw a new circuit that's going to have R1 is going to have some new resistor that I figure out the equivalent resistance from this. So I'm going to call this R5, and then I'm going to have R4. And now I've got these that are in series, and I can get to equivalent resistance of one of those. Right, so this is going to be my total resistance for a pretend circuit, right? So I'm going to break it down. I'll deal with parallel in this case first, and then I'll deal with my series and make sense out of it. And I'm going to make an IRV table. My IRV table is going to be huge. Right? I'm going to just put everything on there because then the math becomes really straightforward. Right? So I'm going to have my 3 things I'm going to worry about. I'm going to put everything on there I can think about. So, right, current, resistance, and voltage. I'm going to worry about R1. I'm going to worry about R2. I'm going to worry about R3. I'm going to worry about R4. I'm also going to make up my R5 in here, right? That helps me. And I'm going to have my total resistance. I guess I don't need this. I'm going to have my total resistance, right? So what I'm going to have, and this is 6 different places that I can use IRV to try to get me there. And I'll start filling in stuff that I know, right? So I know that here this is 18 volts. I can calculate this total resistance, and I can figure out how much total current there is. That total current here is going to be the same for 1, 5, and 4. Right? So current, current, current. And that voltage across 3 and 2 are going to be the same as it is for R5, right? So I can calculate my voltage at 5, and that's going to be the same as my voltage across each of these. And I know these resistors, right? This is 10, this is 5, this is 6, this is 7, this one I have to calculate, and this one I have to calculate. So anyway, I hope you see that it becomes a Sudoku puzzle way to try to tackle complex circuits. But if you break it down and you lay out an IRV table, then it's just the same calculation over and over again using a couple of rules. Hope it's helpful. Good luck. Talk to you soon. Bye.